Oh, there we are. 20 it is.
Bingo, 21.
Yep. Alrighty, everybody, I'm going to go ahead and get started because I know we have a full presentation. I'm going to make sure you all get all the information and that you are able to ask questions. And again, I know we do these as state as lunchtime series. And so we start them at noon because we know a lot of you all typically get maybe an hour for lunch from 12 to 1. And so we want to make sure that you're all able to get as much of the material as possible. But know that this actual seminar is blocked for an hour and a half, so 12 to 1:30. So please feel free to ask questions as we go along. I will be monitoring the chat to make sure if you guys want to put things in the chat, but always feel free to come off mute. For those of you who don't know me, my name is Dr. Joni Rixodi. I am the director for two units of statisticians on campus. So one is the UCI Center for Statistical Consulting, which is in the statistics department. The other is the BIRD unit, which stands for Biostatistics, Epidemiology, and Research Design Unit. And that is in the Institute for Clinical and Translational Sciences. We are a group of epidemiologists and statisticians on campus that consult with faculty members and researchers on campus and in kind of the broader kind of regional Orange County area to support research projects, do data analysis, help with study design. We support grant applications. We do coursework like this in order to equip you all to be the best versions of yourselves when it comes to doing high quality research. I am joined today by one of my favorite instructors, Dr. Chuck Huber. I've known Chuck for a longer time than maybe both of us would like to admit, but he works for
Probably.
Stata Corp and has a wealth of background in just the different the different functionalities of Stata, the different types of analyses, and also methodologies behind them. So use him as a resource, ask for questions. He's very approachable, has been doing this for several decades, and so and is we're lucky enough to have him come and do these seminars for us for free. So without further ado, I'm going to turn it over to Chuck.
All right. Thanks, Joni. And thank you, all of you, for being here. I did post a link into the comments window that has a link where you can download all the materials, the slides, the data sets, the do files, and all of that. So in fact, I'll do it one more time since people have come in. There we go. So you can download all the materials. Okay. Let me share. Actually, let me mute my video here. Share the slides, and we'll be on our way. Are the slides showing up okay? I'll take that as a yes. No one's complaining.
I gave a thumbs up.
Okay, cool. Um, okay, so today we're going to be talking about causal mediation, and this I think is the last talk in sort of a series on causal inference. Although I think we're going to be doing SIM later on, which is kind of related to causal inference. So continuing on with causal inference, today is going to be causal mediation using Stata. Again, you can download all the materials, the slides, the data sets, and the do files at this tiny URL. And again, I posted that in the chat window, so you can just click on that. I do want to acknowledge Aram before I begin. I saw an early version of his webinar on this topic before I created my workshop on it. And it was so good. The problem is once you see something that good, it's hard to get it out of your head and do something original. And so a lot of what I have here is either heavily inspired by or directly copied from him. Some of these are actually his slides that he gave me permission to just borrow because they're so good. And so this talk is heavily inspired by Aram, and so I wanted to just acknowledge that. So here's what we're going to do. The title is causal mediation, and so those are two words that each have their own sort of background. So I want to start off talking about causal inference, and we've done this before. We did this, I believe, two months ago. We talked about the treatment effects estimators in Stata, and so I want to briefly review that and talk about the ideas of causal inference. And then we're going to introduce just plain old mediation, just to wrap our heads around what mediation is. And then we're using structural equation modeling. And then we're going to put those together with the new mediate command that came out in Stata 18. I have continuous binary and count outcomes in here. but we're not going to have time to go through all of that. I originally wrote this as a 3 hour workshop, and I've I've tried to trim it down as best I can, but there's just not enough time to do all of these things. So we're going to cover the continuous outcomes with mediate at the end. I've left the slides in for binary outcomes and count mediators. So the slides are in there as well as the all the material is in the do file. So it's really about 3 hours worth of material in the download. But I'm going to stop with continuous outcomes today because we just don't have enough time to cover all of that. Okay. Excuse me. As I usually say at the beginning of these, if you have questions, please just unmute your microphone and jump right in. It gives me a chance to grab a sip of water, and we don't have to go hunt for slides later on. I'd rather just answer questions as we go. And if you can't unmute your mic, just type them in the Q&A window, and I think Joni may relay them along to me. So, and I'll pause periodically and ask for questions. Okay. So let's talk about causal inference first. Just as a quick review, for some of you, this may be new, but if you've been attending these, some of this will be familiar. So, causal inference, as the name implies, tackles the fundamental question of cause and effect. And with the idea of cause and effect, we're interested in comparing the outcome when some action T is taken versus the outcome when some action T is withheld. And here we're using this do operator that comes from the causal inference world. So we do some treatment, and that treatment could be something like a drug intervention, a vaccine, and it could be a social media, the effects of social media, some exposure. It doesn't have to be an assigned treatment. It could be an exposure like social media or genes. And we're interested in the effects of these things on some outcome. So again, we might be interested in the effect of a drug on a disease, or social media on mental health, or genes on a disease, or things like that. But we're interested in causation here, not association. Association is one thing, but causation is more information. And as we've always been taught since the very beginning, association itself does not necessarily imply causation. There are lots of examples where we have strong associations between things, but it's not really causal. So, for example, a treatment could be something like sleeping with your shoes on. So let's say we're interested in the effect of sleeping with your shoes on, and the outcome could be waking up with a headache or not the next day. And so we study this and we find that most of the time when somebody sleeps with their shoes on, they wake up with a headache. And so the question then is, can we interpret this relationship as a causal relationship? Is there something about wearing your shoes when you go to bed that makes you wake up with a headache? Well, you think about this and study it a little more carefully, it turns out that drinking a lot of alcohol the night before is associated with both sleeping with your shoes on and waking up with a headache the next day. So, in fact, it's not the sleeping with your shoes on that causes the headache the next day. It's the drinking that causes both the sleeping with your shoes on as well as the headache the next morning. So really, the drinking is the causal thing, but we're going to refer to it as a confounder, and this kind of association is confounding association. So again, it's different from association. It's there can be an association where there's no real causation. So a little bit of notation here. We're going to refer to T, and T is for now going to be 0 or 1. We're going to expand that later, but for now, T is going to be treated or not treated, or exposed or not exposed. It's going to be binary. So that's what T represents. And in this case, it could be wearing shoes or not wearing shoes to bed. We're going to use Y to denote the outcome. Y is kind of the universal outcome letter, so we're going to stick with that. And then X is going to be a potential confounder that may have some effect on both T and Y. In our example, maybe something like drinking the previous evening. Okay. So we can draw these as something called a directed acyclic graph, or DAG for short. These are very popular in the world of causal inference. They do look like structural equation model path diagrams, and they are related in some ways, but they are subtly different as well, particularly with regard to that do operator. There's a concept of a do operator in causal inference and DAGs that we don't have in structural equation models. But anyway. So we're going to use these diagrams to sort of draw the causal relationships that we're exploring. Okay. So in this case, we have Y as the outcome. We believe T causes the outcome Y, and then we have X that may or may not be a confounder because of its relationship with both T and Y. Okay. Now, we're going to be using something called the potential outcomes framework to do this. And so, one of the problems is that we only observe people under one of the conditions. We only observe people either as treated, or we observe them being not treated. We can't really observe them under both conditions. What would be wonderful is if we had a time machine where we could observe your outcome when you're treated and then rewind time and then send you back through time again as untreated and observe the outcomes under both conditions. But we don't have time machines and we can't do that. So, what we're going to do, let me fast forward to some slide. Here's the slide that actually makes a little more sense out of this. So, the top triangle is what we actually observe in the real world. Okay, so we observe this relationship between X, T, and Y as the person was actually treated. Now, the middle triangle, the middle diagram, we're going to use this sort of notation where notice I've split the treatment circle in half, and everyone, there's a zero inside the little semicircle pointing towards Y. What this diagram represents is we're going to assume, or we're going to set everyone in the data set equal to zero or not treated. We're going to make the assumption that no one in the data set is treated and examine their outcome. And then in the bottom triangle or the bottom diagram where it says one, there's a semicircle with a one as part of the treatment circle. We're going to assume that everyone is treated and observe their outcome. Okay. So if this is a little bit kind of hazy, here's another way to look at it. The top circle is what we observe. Okay. So some people are treated, T equals one, and that's the white side of the circle on the top circle. And the blue side is T equals zero. And notice they don't have to be equal. You may have fewer people who are not treated, more people who are treated. They don't have to be equal. On the right side is what we would call association, and mathematically, how we would represent the idea of association. We're talking about the expected value of y given that they were actually treated. We want to calculate the expected value based on how the people were actually treated or how they were observed. And on the right side, I have the blue half circle. That's the expected of y given that people were not treated. So we take the people who were actually not treated and calculate their expected value of y. And if we calculate the difference between those, that gives us some measure of association. Is there a difference given their observed treatment statuses? Causation is different. And to me, this is really what differentiates association from causation. On the left path, the left arrow points down to causation, and notice that the left circle is entirely white. Again, we're going to assume that calculate the expected value of y, assuming everyone is treated. And then we have the blue circle on the right. We're going to calculate the expected value of y, assuming that no one is treated. Now, again, if this seems a little weird and is kind of abstract, we're going to walk through an actual concrete example of this. And hopefully this will make this a little clearer. So let's start off by doing this. So I have this data set. I've named it NHANES 2015. And again, you can download this and work with it. And it contains three variables. I have SBP, which is systolic blood pressure measured in millimeters of mercury. And then I have a person's weight measured in kilograms. And then I have a variable called meds BP, which is an indicator for whether or not the person is taking hypertension medication. Now, I want to emphasize that this is not a clinical trial. This is not an experiment. This is just purely observational data. It comes from the NHANES study, the National Health and Nutrition Examination Survey. So it's observational data, not clinical trials data. So people were not randomly assigned to take medication. This is just how we are observing these people in the population or in our sample. Okay. So this is the raw data for the first 10 people. I have whether or not they're on meds, yes or no. And the middle column, weight, is their weight measured in kilograms. And then I have SBP, which is their systolic blood pressure, millimeters of mercury. That's the raw data that I have. That's what I observe. So before I start doing anything, I like to look at some just exploratory graphs. So these are box plots of systolic blood pressure for people who are medicated on the left, who are taking systolic blood pressure meds, and people on the right who are not. Notice the people who are not taking meds, it looks like their blood pressure tends to be a little bit higher and a little slightly less variable, but again, we're just kind of getting to know our data. Now, another thing that I could do is I could do scatter plots for the relationship between weight and systolic blood pressure. So here the horizontal axes are of both of these graphs. The horizontal axes are weight in kilograms. The vertical axis is systolic blood pressure. And the graph on the left is for people who are not taking blood pressure medicine, and the graph on the right is for people who are taking blood pressure medicine. And what I've done is I've fit linear regression lines for each of these. I've plotted a line through each of these. And notice that on the left, people who are not taking blood pressure meds, there seems to be an upward association between weight and systolic blood pressure. So the more you weigh, the higher your blood pressure tends to be. But on the right side, it looks like there's an inverse relationship between weight and systolic blood pressure for people who take blood pressure meds. Well, why might that be? Well, maybe people who weigh more are taking a higher dose of blood pressure medication. So the heavier you are, the stronger the medication, and that's going to bring your systolic blood pressure down. I'm just speculating here. This is just descriptive in terms of the scatter plots, but that's something that we observe when we do this. So, how do we actually, that's just basic sort of association. So let's walk through this and look at how we would do this with causal inference. So I observe in this top box, the first five observations here, I observe their systolic blood pressure under the condition that they were not medicated. Okay. And so I can move that to their observed systolic blood pressure. I've just copied systolic blood pressure to OBS SBP 0. So that's what I observe. I don't observe their systolic blood pressure when they are treated. Okay. That's just missing data. And similarly for the observation 6 through 10 here, I observe their systolic blood pressure when they are taking medication, blood pressure meds, but I never directly observe them when they're not taking blood pressure meds. And so in a way, this is like a missing data problem. I have some missing data and I need to fill it in. So how are we going to do this? Well, I'm going to fit a regression model that looks at the relationship between weight and systolic blood pressure only for people who have not taken blood pressure meds. So if meds BP equals 0, and I'm going to fit that regression model and I'm going to take those coefficients. So I have the intercept and the slope here. I'm going to generate a new variable called exp underscore SBP 0. And I'm going to use the intercept and the slope to estimate the expected systolic blood pressure, assuming that no one in the data set is treated. Everyone is untreated. Nobody is taking meds. Okay. So that's what that expectation is that I've generated at the bottom using those regression coefficients. Okay. So now if I look, I have a value of the expected systolic blood pressure, assuming no one was treated. I have that expectation for everyone in the data set. Everyone gets a value. I'm not missing any data there. Okay. So that's what we're going to call our potential outcome Y0. That's what we expect, assuming that no one was treated. Okay. Now let's repeat this for assuming that everyone is treated. So I'm going to fit the regression model only using the people who were treated, excuse me. I'm going to fit the regression model only using those people who actually did take blood pressure meds. And then I'm going to use the regression coefficients from this model to generate the expected value of systolic blood pressure, assuming that everyone was treated. Okay, so I'm going to use the intercept minus the slope times weight. That gives me that expectation. So now if I look at my data set, I have the expected value for systolic blood pressure for everyone in the data set, assuming that everyone was treated. So the holes in my data, I have the observed values, and now I have the expected values under those two conditions. Well, now this is almost like using a statistical time machine. I can sort of rewind and say, okay, what would the expected systolic blood pressure be if everyone was not treated? What would the expected systolic blood pressure be if everyone was treated? So now I have those two potential outcomes. And what that allows me to do then is I can calculate the difference between them. Okay. So these are the potential outcome means. If I calculate the mean of those, I have the mean or the expected systolic blood pressure, assuming no one was treated. That's 128.3497. And then I have the expected value of systolic blood pressure, assuming everyone's treated. That's 134.9. Okay. So those are the means. What I can do then is calculate the difference between them. So this TE is going to be the treatment effect, and that's the difference between those two expected values. Okay, and then if I calculate the mean of that treatment effect, it's 6.56. So what that's telling us is that assuming that everyone in the population was treated, and then assuming that no one in the population was treated, the difference between those expectations is about 6.5 millimeters of mercury. And we're going to refer to that as our treatment effect, or actually the average treatment effect, or ATE. Okay. So we've seen this kind of before. We've done this back when we talked about treatment effects RA. This is essentially doing T effects RA, or using that. So I could have done this with Stata's T effects RA command and set up the syntax like this, or use the dialog box. And what this will do, if I do T effects RA, that gives me these potential outcome means. And if I look at the bottom, those are the potential outcome means that I calculated just manually using my regression. And notice that they're the same out to 4 decimal places. Actually, yeah, out to 4 decimal places, three on one of them, but it's just rounding differences. So it's the same thing. We could have used T effects RA to do this. And if we wanted to see the treatment effect, same thing. We could have used T effects RA to calculate the average treatment effect, or ATE, or we could have done this just by calculating the mean of our TE variable that we created manually. So that's what the T effects RA command is doing for you. It's doing all those steps behind the scenes to calculate those potential outcome means and the average treatment effect. Now, just as a sneak preview, we're going to come back to this later, but there's a way to do this with the new mediate command as well. So that's the thing we're headed towards. So sneak preview, we get basically the same thing. They're off slightly because of some uh, slight differences, but essentially you get the same thing using mediate. But we'll come back to that. We're not to mediate just yet. Just kind of a spoiler alert there. So that's the basic idea of causal inference. So, any questions up to here? I know this is kind of review if you've been to the other talks, but I like for this to be kind of self-contained. Any questions? Okay, so let's move on to mediate. And this is going to be probably new for many of you. I'm going to start off just with the ideas and use regress, and then we'll ramp up into using sim and sim bootstrap. I put this in here. I'm not going to read the whole definition to you. It comes out of a very popular book because to me, the definition is a bit kind of confusing. To me, it's easier to think of things with examples. And so, here, continuing with systolic blood pressure, let's say that I'm still interested in systolic blood pressure. And now I'm interested in the effect of age on systolic blood pressure. So rather than having a medication, a binary medication, I'm interested in the continuous variable age. So it's fairly well known that as we age, the older we get, our systolic blood pressure tends to go up. Even controlling for other things, it just systolic blood pressure goes up with age. But we also know that there is a relationship between age and weight, that as we get older, we have a tendency to put on weight. And as we gain weight, the higher our weight, the higher our systolic blood pressure tends to be. And so there is this direct effect of age on systolic blood pressure, but there's also a sort of indirect effect of age through its influence on weight. You get older, you weigh more, your systolic blood pressure goes up. So we have the direct effect of age on SBP. We have the indirect effect of age on SBP through its influence on weight. And that's what mediation is all about. We're interested in quantifying these direct and indirect effects. Well, first, asking the question, is there a direct and indirect effect? And if there is, then how are we going to quantify that? So, assuming that there is an effect, or for measuring these things or quantifying them, we're going to label these paths, these arrows, with some letters. So, for whatever reason, we call the direct effect C prime. So the direct effect is the C prime. The indirect effect is going to be A times B. So whatever the effect of age is on weight, that's A. Then whatever the effect of weight is on SBP, we're going to call B. So the indirect effect is the product of A times B. Now, this I think is confusing in the beginning, and so let me see if I can make sense of this. A is just a regression coefficient, and B is also a regression coefficient. And if you remember how we interpret regression coefficients, each additional year of age increases weight or is associated with an A increase in weight. So each additional year of age is associated with an A increase in weight. Well, if that's the case, and remember that each additional kilogram of weight is associated with a B increase in systolic blood pressure. Well, if that's the case, increasing age by 1 year increases weight by A, and increasing weight by A by one would increase SBP by B. So it's a multiplicative relationship. Okay, so that's why we multiply A times B. Okay, so that's the indirect effect. And then the total effect of age on SBP is the sum of the direct and indirect effects. So it's going to be C prime plus A times B. Now, in the old days, this was done with regression analysis. I'm going to use the same data set, but I'm going to be using age this time as the treatment, as a continuous treatment. So we could do this, and this is how it used to be done in the old days, was with regression modeling. And so what I'm going to do is have two separate models. One is systolic blood pressure as the dependent variable, and I'm going to include both age and weight as covariates in that model. And in that model, C prime is the coefficient on age and B is the coefficient on weight. And then I fit a second model where weight is the dependent variable, and the coefficient for age is A. That's the effect of age on weight. So in the old days, what we would do is fit these two regression equations, and then we would save them. So here I fit regress, weight, and age, and I need to make sure that we're only fitting this model for people who have some value of SBP. They're not missing SBP, so the sample sizes match. And I'm going to take that age coefficient and call it A. I'm going to store it temporarily using scalar A. And then what I'm going to do is fit the second regression model for SBP using age and weight as predictors. And I'm going to grab those coefficients and store them temporarily as scalars. So this 0.429, that's going to be the scalar C prime, and 0.13487, whatever, that's going to be scalar B. Okay. So we're going to store those. And then what I can do is just do the arithmetic. So at the top, I'm just displaying here the direct effect of age on SBP is, and I'm going to display C prime there, 0.429. The indirect effect of age on SBP, well, that's the product of scalars A and B. So that's going to be 0.05. And then the total effect of age on SBP, that's going to be the sum of C prime plus the product of scalars A and B. So that's 0.4827. So what do we do with that? Well, we don't have confidence intervals or any standard errors. We can't really put a p-value on that, but we can describe it. So we've made it that far. Okay. So how do we interpret these? Well, we could say then that the direct effect of age on SBP is the estimated coefficient for path C prime, which is 0.429. So each additional year of age is associated with a 0.429 millimeter of mercury increase for systolic blood pressure. The indirect effect, I'm just going to read the last part of it. Each additional kilogram increase of weight is associated with a 0.135 millimeter of mercury increase in SBP. So the estimate of the indirect effect is the product of those coefficients, which equals 0.053. And then the total effect is the sum of those two, the direct and indirect effects. So the problem there, though, is that we don't have standard errors, so we can't calculate t-statistics or confidence intervals or anything like that. So we need to find a better way to do this. Another way to do this is with Stata's sim command, and there's a post-estimation command called estat effects that will then calculate those effects for us. So what we can do is open Stata's sim builder and draw this as a path diagram. So if you're not familiar with structural equation modeling and path diagrams, this allows us to draw these. The measured variables, the observed variables, have corners on the boxes. So I have age, SBP, and weight. And then the arrows that connect the boxes are like regression coefficients. So we're going to use structural equation modeling to estimate those parameters. And we'll be using maximum likelihood. This is the sim estimation window. And we can see the values of C prime, A, and B on the actual path diagram. This is done in Stata in the sim builder if you've never seen it. So again, our estimate of C prime is 0.429, our estimate of A is 0.396, and our estimate of B is 0.135. So what we could do then is we noticed that with SIM, we fit the entire model simultaneously. Remember, with regress, we had to fit two models separately. But here we can fit both of those models simultaneously and estimate all of the coefficients at the same time, which means that we also get standard errors simultaneously, estimates of the variance of the error terms, and all kinds of things like that. But recall, we're not really interested in the coefficients themselves. What we're interested in are those direct, indirect, and total effects. And we can get that by after we fit our SIM model, we can type E stat T effects for treatment effects. And what this will then give us are the direct effects, the indirect effects, and the total effects. Just automatically, you fit the SIM model and then type E stat T effects and you get all this. It's hard to read when it's that small, so I've blown it up here a little bit. So this section on the right, the table on the right, is the are the direct effects from E stat T effects. This middle section here, the table on the right, is the middle section of the output, and that shows us the indirect effect. And at the bottom, we see the total effects. Now, notice in these tables, not only do we get a coefficient, but we also get a standard error, a z statistic, a p-value, as well as a confidence interval. So if we wanted to report these in a manuscript, not only do we have an estimate of the effect, but we also have a confidence interval for those, or we could put a p-value on them. Okay, so that's something much more useful that we could do. Now, there is a slight issue with doing it this way. People have done simulation studies and theoretical work to show that maximum likelihood may not be the best way of getting treatment effect, getting standard errors for the treatment effects. And so, an alternative method for estimating this is using bootstrap standard errors. So let's go back and take a look at our sim command here for a moment. So sim, I can fit the model, estimate the coefficients. And if I type coef legend as an option at the end, what that will do is show me a legend of how these coefficients are stored in Stata's memory after we fit the model. So I fit the model, and I can actually refer to those coefficients using the legend here on the right. So for instance, the weight coefficient is underscore B and then SBP colon weight and square brackets. The first variable in the square brackets is the dependent variable or endogenous variable in that part of the model. And then the right side is the exogenous variable. Well, I guess in this case it's endogenous because it's in both. But anyway, it's the covariate or the predictor for that part of the model. Okay, that section of the model. So we get all these coefficients. We can refer to them after the fact using this legend. So what I'm going to do then, Stata has a command called bootstrap. And what that allows me to do is specify equations or combinations of the coefficients in the model, and it will use bootstrap standard errors to estimate the standard errors for those whatever quantities I specify. So this is one giant Stata command. It starts off with bootstrap, and then I have three lines right after that. The first is direct. The direct effect is going to be the coefficient for systolic blood pressure and age. SBP is the outcome or endogenous variable. Age is the predictor variable or exogenous variable. So that's going to be the direct effect there on the first line. The triple slashes tell Stata that this command continues on the next line, and then I have the indirect effect. So remember, the indirect effect is the product of coefficient A and coefficient B. And so that's the product of those, and I've used the legend notation to refer to those. And then the total effect, the third line, that's going to be the sum of the direct effect plus the indirect effect. On the fourth line, I've typed no dots. Note every time it does an iteration or draws a new bootstrap sample, it'll put a dot on the screen. And I didn't want to watch that for all of these, so I put no dot, use the option no dots. And then I type colon and then type the name of, or type the sim command. And what that will do then is run that sim command, repeatedly drawing bootstrap samples and construct standard errors from those. So when I run this command, this is what I get. So the results at the bottom show me the observed coefficient for the direct effect, the indirect effect, as well as the total effect. And I get bootstrap standard errors for these. And these bootstrap standard errors are then used to calculate p-values and confidence intervals. And again, simulation studies and some theory has shown that this actually gives us better estimates of the standard errors than using traditional maximum likelihood. Okay. So that's how we could do just plain old mediation. Okay. Just mediation by itself. So any questions up to here?
Oh yeah, Chuck, we have a question in the chat. Ellistina, do you want to come off mute and ask your question?
Sure. I'm not sure. Are you able to hear me?
Yes.
Yes, I can hear you.
Wonderful. I wanted to understand if mediation is a kind of a Fisher-Lover theorem, because I guess both of them are dealing with decomposition of the variables to actually get the treatment effects. Is it a kind of that theorem?
Is it a kind of what? What's the last word you said?
It's the I've never heard.
Fish waggle,
Yeah, go ahead.
I'm sorry, I couldn't hear it again.
fish waggle level theorem. I've written it in the chat.
It's the Free-Schwa level theorem.
I have not heard
Yeah.
that before.
I had not either. When I looked it up, it was
Just
it looked like it was essentially like a version of two-stage least squares. This is just like a quick Google. I have not heard of this theorem either.
I've never even heard that term before, so it looks like I get to learn something new today. In fact, before I lose it, I'm going to copy that. Oh, whoops, I can delete it. No, I'm gonna have to go look that up. I'm not even familiar with that. Is that something from mathematical statistics, or I just don't know.
Uh,
I've not heard the term.
Look at something from econometrics.
Oh, is that what it's from?
yes, it is econometrics.
Okay, that's why I've
Basically,
never
you
heard it.
want to understand. Yeah. Ah, okay, fine. Okay. Thank you.
Okay. Yeah, I have zero training in econometrics. I think Joni has a bit more than I do, but that's a new term for me. I'm gonna have to go look it up.
Yeah, I had to Google it myself.
Okay, can I just write this down really quickly because I need to go learn a new word today. Frisch, wa level. Okay, I will go look that up. And if you want to email me, my email address will be in here later, and we can talk about that once I educate myself. So thanks for that. It could be. You may be right. In fact, you're probably right. I just don't know enough to answer that question. But thanks for the question because it gives me a chance to learn something new today.
No,
Does anyone
thanks to
else
you.
know?
Thanks.
We probably have a lot of smart people online today. Anybody have an answer to that question? I guess not. Okay. We'll look that up. I will look that up. And then if you'll shoot me an email, we can discuss that later on. But thanks again for the question. Any other questions?
Chuck, this is Mark. I have a question about
Yeah,
some of the standard errors. Is it possible to calculate robust standard errors using any of these methods?
I believe you can with sim. And can't remember if you do this with sim, if that propagates into the E-stat T effects calculations or not. I don't know off the top of my head. Uh, I'm trying to think. I don't know how to get to the sim. Remind me at the end, and I can look that up in Stata. I mean, that'd be quick to find out because all I have to do is open the dialog box and look and see under the sim estimation dialog if that's an option. I don't even have to go read the manual. I can just check the dialog box.
Okay,
Remind me at the end, and we'll take a look at that because that's an interesting question. I'm pretty sure the answer is yes. You could use robust standard errors.
will do.
Any other questions? Okay. So, kind of like the old, most of you are probably not old enough to remember the old Reese's peanut butter cup commercials where two people are riding in a car with a candy bar and a jar of peanut butter and they hit a bump and they end up with the chocolate and the peanut butter. And anyway, that's what we're going to do now. We're going to take the chocolate and the peanut butter, the causal inference and mediation, and we're going to put these together. We're going to combine them into one thing. So, the concepts of both continue on. Okay. But what we're going to start doing is we're going to do mediation using the potential outcomes framework of causal inference. And that would be kind of challenging. I'm going to show you how to do it manually because I just like doing that. It helps explain it to me, what's going on behind the scenes. And I'll show you how to do this with the new mediate command that came out in Stata 18. So this is the dialog box for the mediate command. This is way more powerful than what you can do with sim and gsim. Um, so do this. What I'm going to show you with gsim here in a moment allows you to sort of recreate it for certain scenarios, but the mediate command is very, very powerful. So here's the way the dialog box is set up. At the top in the model tab, you have the outcome equation, the mediator equation, and the treatment equation. So if you think back to, where's my diagram? Let me go back to one of these diagrams. Here, I had an outcome variable, I had a treatment variable, and I had a mediator variable. What mediate's going to allow me to do is I'm going to be able to have now an outcome equation. So I have my dependent variable as my outcome variable, but I can have independent variables that are predictors of that. And then for my mediator, I don't just have a mediator variable, I actually have a mediator equation where the dependent variable is the mediator, but I can have other independent variables or predictors of that mediator. And I have the treatment equation, so that can be an equation as well. Um, and this allows me to have different kinds of outcomes, mediators, and treatments and things like that. So I can have linear or logit, or I don't remember all of them off the top of my head, but you can have, and you can mix and match these. So you can have linear outcomes, a continuous outcome with a binary mediator and a binary treatment, or a continuous treatment and it's all kinds of combinations of these. So mediate takes what I just showed you in terms of the ideas of mediation, and it ramps this up into all kinds of possibilities. And it does this using the potential outcomes framework. Okay. So this is because this is so flexible and so powerful, we're going to barely scratch the surface of what this will do. So I'm going to kind of continue on with the example I was just doing. I'm going to use systolic blood pressure again as my dependent variable, and I'm going to, for now, just omit any independent variables. I'm going to just recreate what we did with the model we just did with sim. So I'm going to use weight as the mediating variable. Again, no independent variables. And then I'm going to use age as a continuous treatment. Now, because age is a continuous treatment, this is much like using margins. I need to specify values of the continuous treatment. So what I'm going to do is compare a 30-year-old to a 31-year-old, because that's what sim is doing. If you ask it for the effect, it's giving you the effect based on a 1 year interval or 1 year differential in age. So I'm going to use compare a 30-year-old to a 31-year-old in terms of age. So that's it's a continuous treatment, but it's 31 versus 30. Okay. And for now, I'm going to suppress the treatment mediator interaction. That's the other thing that this does that's very sophisticated. Um, so we're going to keep this as simple as we can to replicate what we did with sim. And if we look at this, we run the mediate command. So there are three sets of parentheses. The first is the dependent variable or the outcome. The middle is the mediator. And then the far right set of parentheses is the treatment. And then I've asked it for some things. We're going to come back to what those effects are here shortly because they have different labels in the output. But essentially, the top one here that's labeled AITE, that's the direct effect. And again, we get, in this case, Mark just asked the question about robust standard errors. Here, by default, you get robust standard errors. Okay. And so we get the coefficient, robust standard errors, a z-statistic, a p-value, and a confidence interval for the direct effect, as well as the indirect effect, as well as the total effect. Okay. So it's a different way of doing this. And here what I've done is simply replicated what we did with sim. Okay. Just to make it easy. But this is far, far more flexible than the sim command when it comes to doing this. Now, there's also an A equations option. A equation stands for auxiliary equations. And so what I've done now is I rerun this mediate command, and what it's doing is it's showing me the actual auxiliary equations. So it's imagine that we actually fit those regression or fit the sim model underneath, and it's showing us the age coefficient for SBP, the weight coefficient for SBP. Now, notice there's an interaction in here. There's a weight by age interaction term in that SBP model, as well as an intercept. And then we have the weight model. This is just like what's going on with SIM in the background. The only difference is that it's including this interaction term between the mediator and the treatment. Okay. So in this case, I've allowed it to do that. I've removed that no treatment mediator interaction. So if I do that, what that's effectively doing, well, let me go on with the syntax here for a moment. We'll come back and I'll show you what it's doing under the hood. So again, this is the dialog box that allows you to fit all kinds of models. The basic syntax is just like what I just said. The command is mediate. The first set of parentheses, excuse me, are the outcome variable and any outcome predictor variables, OM var list. The middle is the mediator and any predictors of the mediator. And then T, the third set of parentheses, is our treatment variable. And if it's continuous, we need to give it a num list. So that's the basic syntax. You can, as I mentioned, you can do all kinds of combinations of these. So if I have a linear outcome, I could have a linear mediator, a logit mediator, a probit, Poisson, or expected mean mediators. If I have a logit outcome or binary outcome, I can use a logit mediator, probit mediator, Poisson. Probit, I can have a linear mediator. You can read the chart. Lots and lots of combinations of these in here. So this is far, far more flexible than doing this with status sim command and estat t effects. Very, very powerful and flexible. Now, one of the other issues that came up in working on this is the causal inference world has not really standardized. It's a fairly new world, and there are different camps. And one of those camps is kind of the Judea Pearl DAGs approach. And that camp has their own terminology. They call things natural indirect effect, natural direct effect, pure natural indirect effect, and that sort of terminology. And in the statistics world or in the econometrics world, they use this average treatment effect or potential outcomes terminology, and they refer to things as average indirect treatment effect, average direct treatment effect, and so forth. We couldn't decide how to label the output because we were going to make someone unhappy. So what we've done is we've given you a choice. You can label these however you want. So if you go under the stat tab, you can check the boxes that use Judea Pearl's terminology, or you can check the boxes that use the average treatment effect or the potential outcome means terminology. So you can choose to label the output however you are, whatever's familiar for you. Okay. Now, I'm not going to read all of these to you, but this is why we have all those funny letters as options at the end of the mediate command, because these are the actual option names if you check these boxes. So all of this natural stuff, that's Judea Pearl terminology, and all the average terminology, that's the potential outcome means stuff. Now you can just specify all. If you can't decide or you're not familiar with these, just specify all and it will report them all, and then you can look up the meanings of them. Okay. So for causal mediation, what we're referring to then is before we had an outcome, a treatment, and a possible confounder. Now what we're going to have is that same setup, but we could have a mediator in here as well. So our confounder could influence any of these things. The confounder could influence the outcome, the mediator, or the treatment. So that's what's going to complicate this a bit is that now we're combining confounding and mediation all in the same model. Okay. And so we're going to have to take these things into effect. Now, when we do this, before what we did was we said, well, I'm going to assume that everyone got the treatment and sorry, on the left, it's no one got the treatment. On the right triangle, it's everyone got the treatment. And that's how we calculated the potential outcome means. But now we also have to take into account the mediator. And so we have these various combinations of the mediator and the treatment, assuming no one was treated or assuming everyone was treated. And so that's what we're going to start seeing these combinations of Y1 and M1. So that would refer to Y, assuming everyone's treated. And the M1 means the mediator, assuming everyone was treated. And then we got a Y1, M0, meaning Y1, assuming everyone was treated for the treatment, but M0 would be the mediator, assuming no one was. And all of these have meanings to them. And I don't really have time to go into all of that here. I recommend you go read the manual because it's kind of deep and it's a lot to take in. But what we can do then is calculate these potential outcome means under these assumptions. Everyone treated, no one treated. So what I can do then is type mediate just like I did before, and I'm going to type PO means. So rather than seeing all those effects, what I want to see are the actual potential outcome means. So that's where was where I mentioned we get these Y0 M0, Y1 M0, Y0 M1, and so forth. Now, to me, this was a little confusing at first, and so I needed to kind of explain it to myself. What's actually going on here? Because I'm combining now the ideas of mediation with causal inference or these potential outcome means. So what I did, and I don't know if this will help make sense of this to you or not. I went back to GSIM and I wanted to work this using GSIM to see if I understood what was going on. So here what I'm doing is I'm going to use Stata's GSIM command for generalized structural equation models. And I'm going to fit that model just like I did before using GSIM. But remember, I have to have that interaction term in here. Mediate, I could fit it without, but I want to see how this works even with the interaction, because that's what mediate does by default. So I have these two models, those original regression models. So systolic blood pressure is the outcome, age is the treatment, weight is the mediator. So I fit the first model here in the first set of parentheses, and then I have the influence of age on weight in the second set of parentheses. And again, this is just GSIM. The listwise option tells Stata to use listwise deletion of observations. Let's not go into that today because we're running out of time. But that makes it match the results of what we get with mediate. It's how Stata is handling missing data across those equations. So if I use GSIM, I get these coefficients. And then I get this legend. Remember, we have the legend that refers to these coefficients, and we can refer to those after we fit the model. What I'm then going to do is use Stata's nlcom command. That's short for nonlinear combinations of parameters. So I'm going to calculate the Y0 M0, that potential outcome mean we saw in the mediate output. How is that calculated? What I'm going to do is do this calculation assuming that everyone is 30 years old or everyone is not treated. And so this is how that calculation is actually done. So Y0 M0 is going to be the intercept for the SBP model, the age coefficient for the SBP model times 30. So that's times 30. That's assuming everyone is 30 years old. Okay. Remember back when we did this with just good old regression? We substituted in zero. We assume everyone is not treated. So that's what that 30 is there for. The third line, I have the coefficients. And again, for the treatment, I'm going to substitute in 30, assuming no one is treated. And then the fourth line there of the equation, again, I'm substituting in 30. I'm assuming no one is treated. Everyone is 30 years old for the calculation of the potential outcome mean of Y0 M0. Okay. So that's how I would calculate that using GSIM and NLCOM. Let's do it one more time, assuming everyone is treated. So now what I have is I'm going to substitute in, it's the exact same equation I had before, but I'm substituting in 31. Everywhere I have to put in an age in the calculation, I've put in a 31. So I'm assuming everyone in the data set is treated. And that gives me the potential outcome mean for Y1M1. Okay. And then if I go back, I could actually do that for all the combinations, Y0, M0, Y1, M1. That's what mediate is doing for us. It's doing all these calculations in the background, and that's where those potential outcome means come from. So if this is a little confusing, all of this is in the do file. This will walk you through exactly what mediate is doing behind the scenes and how those calculations are done. I find it helpful to see how the calculations are done. Maybe it helps you. Maybe it's just confusing. I don't know. But it's there if you want it to see where those come from. Now, why do we care about those potential outcome means? Well, all of these effects, the direct and indirect effects and their variations, are functions of these potential outcome means. They're just differences between those potential outcome means under those different conditions. So if I can calculate those four potential outcome means, I can calculate all of those effects manually. They're just differences. So I have things like the total natural indirect effect, or NIE. I have the pure natural direct effect, or NDE, the pure natural indirect effect, PNIE, total natural direct effect, TNDE, and then the total effect, TE. So that's one way of describing those. So those are all just differences between the various potential outcome means. So here I've rerun this using mediate and then labeled them so you can see NIE and the output. So you get the potential outcome means at the top as well as each of the effects at the bottom. Okay. So now we know how all of these things are calculated. Now, the real trick here, understanding the math is one thing, understanding what they mean is another. And again, I'll leave that to you to either read through the manual, the examples, because the ideas are the same. You still have an indirect effect or a direct effect, but they add these labels to them: pure, natural, pure, whatever. And again, these are differences between the way Judea Pearl uses the language and the way the potential outcome mean people use the language. Uh, anyway, and we're almost out of time, so I need to move on here. So the obvious question then becomes, which of these decompositions should I use? They're all now I have four potential outcome means, and I have all these decompositions. What are they, and how? When should I use them? So one of the Wynn paper describes basically three different cases or ways you should use these decompositions. Case one is just asking the question, is there a mediated effect? Is there any mediation going on? Because if there isn't, then we don't need to take mediation into account. So if that's the question, if the question is there a mediating effect, then they propose using this del one and this NIE, the natural indirect effect and natural direct effect. Use those. And the rationale here is that they're not questioning the existence of the direct effect. They already stipulate that there is a direct effect. What they're interested in is there an indirect effect? Okay. So that's case number one. Is there a mediating effect or not? And so that's how we would set this up: mediate and then use the NIE and NDE options, and it will give you those effects. Now, case number two is, in addition to the mediating effect, is there a direct effect? Okay, so it may be possible that there actually is no direct effect. There's actually just an indirect effect. And in that case, we would use this pure natural indirect effect and the TN, which is the total natural direct effect. So the rationale again here is that we're not questioning the existence of a mediator. We're actually questioning the existence of a direct effect. So if I wanted to do that using the mediate command, again, I would type mediate and then use the PNIE option and the TNDE option. Okay. Then the third scenario or third case is that there's no prior assumption. We have no idea whether there's a direct effect, an indirect effect. We're basically admitting complete cluelessness as to the relationships among these variables. And in that particular case, we might as well just run them all and look at them. So if I wanted to do that again with the mediate command, I could either specify, and if you wanted to stick to one version of the language, so here I could do NIE, NDE, PNIE, and TNDE and get those various effects. Okay. Now, one of the assumptions, it's one assumption, it's really kind of one assumption, but they're listed separately as this sequential ignorability. So we need to be able to assume the following. First is that there's no unobserved confounding in the treatment outcome relationship. Second is there's no unobserved confounding in the mediator outcome relationship. Third is no unmeasured confounding in the treatment mediator relationship. You get it. There's no unobserved confounding going on here, no endogeneity going on. And this is sort of in addition to the sequential ignorability and other kinds of assumptions. One of the main ones is the overlap assumption. The overlap assumption is stating that anyone in the data set could have been plausibly in the treated group or the untreated group. If you have some people who could not possibly have been in the treated group, you can't do this because you can't treat them both ways, as though they were treated and as though they were untreated. So again, this is how we would do this with continuous outcomes. After we fit the model, there's a post-estimation command called estat proportion. And what this does is it shows you the proportion of the effect that's due to the mediation, sort of due to the indirect effect. Okay. So that's estat proportion. We'll give you the proportion mediated. And then again, there are lots more variations on this that we can do using binary outcomes and count mediators, and it will do all sorts of other things that you're just going to have to refer to the manual, or someday I'll maybe do a second half of this. But that's what I have for you today. References, here are some references at the end. Sorry, I popped out of the slides too quickly. And again, if you want to download the materials, you can grab that at tinyurl.com/Stata mediation. I pasted this link in the comments window earlier. I can hang around and answer questions for a while, and if you think of them later on, shoot me an email at chuber@stata.com. Okay. So any questions?
Thanks, Chuck.
I know that's a very dense, very confusing topic. It's a lot to take in a short amount of time. So any question again? Any questions?
Don't be shy.
Chuck, this is Mark. I have another question.
Okay.
It's in regards to cluster data. Um, we had like repeated measures or longitudinal data.
Ah,
How does this work? Or is there a different type of Stata command for those?
To my knowledge, you can't do that at this point. This is brand new. This just came out in Stata 18, which Stata 18 isn't so brand new anymore. It's almost 2 years old. But no, to my knowledge, there's no way to handle clustered kinds of data at this point. That would be a cool trick, though, wouldn't it? To be able to do all that and handle clustered or repeated observations.
Yeah, I agree. Maybe it's
Would
something in the works for Stata 19.
I would not want to be the developer on that task. That would be tricky to write because there are a lot of things going on.
Anyone else have any questions?
So, true story, since we're not getting any questions, and this may click on a light for some of you because it did for me. I watch a lot of YouTube, other people's YouTube videos to get ideas and things, and I can't remember the video I was watching, but I was kind of nodded off while I was watching the video, and at some point I thought I heard the video say that mediation was basically just the chain rule from calculus. I could have sworn I heard the person in the video say that. And when I woke up later on, I was like, oh, I never even thought of that. But if you look at it, basically that's what mediation is, kind of like the chain rule. You have an indirect effect of you change one thing and it propagates through the other system. Oh, it's the chain rule from calculus. And then later on, I wanted to go back and watch that section of the video because I knew I had nodded off during part of it and I couldn't find it anywhere. It was not in the video. For some reason, as I was drifting off to sleep watching this video, it clicked in my head. I think I'd been helping my kids with their calculus homework or something, that somehow the beams crossed on my head, and it struck me that mediation, if you've ever taken calculus and you're familiar with the chain rule, mediation is basically the chain rule. The indirect effect is kind of like the chain rule. You manipulate one thing and it manipulates something else through a function into another outcome of sorts. So it's kind of like the chain rule in calculus if you're familiar with that.
So the stats God whispered in your ear,
I
and
guess so.
that's
Because it was not in the video. I went to work the next day and was telling someone about it, and I said, the light clicked on, and they looked at me funny. I said, no, it's in this video. So I went back and tried to find the section of the video, and I couldn't find it. But the person agreed with me. They were like, oh yeah, once you kind of see it that way, it's the chain rule. But anyway,
well, I'll say Google's AI. When I say I Google chain rule and mediation analysis, their generative AI gives you a whole explanation as to why that's the case.
oh, does it really?
It does.
Wow, I've not done that either. I don't have a reference for that. It might make a nice paper for someone, but essentially that's the math going on in the background here with all the fancy stuff. So, sorry, I'm jabbering. Anyone have any questions?
If there's anything in the chat. Nope, just thank yous.
Okay, cool. So we're doing sim, I believe, next time. I have them
That
all.
sounds correct. I don't actually remember what the
No, no, no. I just looked. We're doing survey next time. So intro to survey statistics. That's a fun
okay, so
one.
now we're moving over to survey. Okay.
Yeah.
Okay. And that's when we get
Uh-huh.
a lot. That's when we get a lot as well. So
Yeah. Survey's fun in Stata.
okay.
All
Well,
right. Well, thanks so much. Oh,
everyone.
and I did wear my UC Irvine hoodie again. So
Oh, see there, look at you, always representing well.
that's right.
Are you planning to come out here at all this year, Chuck?
No, I was at Stanford last week, but that was a totally different thing. But no, I am going to do UC Riverside again, oddly the day before you guys next month. But that's all going to be on Zoom. So
Gotcha.
yeah, so I'm not planning to come out there this year. Maybe next year we'll try again. It's been what, 2 or 3 years since I've been out.
It's been a few years since you've been out here, so
And I'd love to try it again, but the thing is, if we do that, we can't do the online part because I
you
keep
have
showing
to
up
be
to
all in
empty
person.
rooms.
Absolutely.
Yeah. So we'll talk about it sometime. But I'd
Okay.
love to come back out. I miss visiting.
Mhm.
So
Okay.
all
Well,
right.
Chuck, we will give you the rest of your 30 minutes back.
Oh, okay.
Thank you again, as
Yeah.
always.
Yeah. Thanks for setting this up. See you next month.
Okay. Bye,
All right.
everyone. Thank you.
Bye.
Thank you.
Thanks,
Thanks.
Chuck.
Bye,
Have a good
Margaret.
one.
Bye, Mark. You too.